Hi, my name is MathYou, and in this video we're going to talk about rational exponents. And don't forget what a rational number is. A rational number is any number that can be expressed as a fraction. So 5 is a rational number because it can be written as 5 over 1. 2/3 is obviously a rational number because it's already a fraction. But what about decimals? How do I tell if they're rational numbers? Here's the trick. If a decimal is terminating, like 0.125, that's a terminating decimal because it ends. Any terminating decimal can be expressed as a fraction. What about decimals that go on forever? As long as it's a repeating decimal, like 0.97979797 and so on, that decimal can also be expressed as a fraction. So that's considered a rational number. So just a quick review of what rational numbers are, as long as we're talking about rational exponents. So as part of a definition of a to the power of 1 over n and a to the power of m over n, let's look first at 1 over n. What we're seeing here is sort of a quick conversion between what is considered exponential notation and radical notation. And the exponential notation is on the left, radical notation is on the right. The number n that you're seeing there, remember, is called the index. And the index is matching up with the denominator of whatever's in the exponent position on the left-hand side. So in this example, we're seeing negative 32 to the 1/5 power. That's being converted to a fifth root of negative 32. And the answer is negative 2 because negative 2 to the 5th power equals negative 32. In the next example, we're being asked to convert the expression to radical form and then simplify if possible. So let's have a look at these. This is equal to the square root of 25. And we could put a little 2 here in the index position, but when we're working with square roots, as I believe I mentioned in the previous video, for a square root, we don't actually write that index, so let's take that away. And we can find the square root of 25. You could write the answer as 5, which would be the primary or principal root. And if you wanted to be even more thorough, you could write plus or minus 5. 16 to the negative 1/4 power. We haven't talked about negative exponents yet, although we're going to in this video. So I will tell you that, in fact, I think I'm just going to hold off on that one, actually. Let's move over to number C, or letter C here, and rewrite this as the third root of negative 27. And I'll remind you that if we have an odd index, and the index here is 3, as long as it's an odd index, we can take or evaluate that for a negative radicand. Negative 27 is in the radicand position. And this is equal to negative 3 because negative 3 to the 3rd power is negative 27. Now when the format changes and it's a to the not just 1 over n, but to the m over n, the m in the numerator acts like a traditional exponent. And farther down in this yellow box, we see a relationship between these different kinds of notation, and while the middle sort of portion of what I've just circled here is true, so it's using the power rule for exponents, I'd like you to focus primarily on the first and third portions of what I circled there. And a to the m over n on the left-hand side of that, you're seeing it here, a to the m over n again, is also equal to this. So you see that the m is on the outside, and here the m is on the inside of the radical. It's actually in the radicand with the a. So in your notes, what I'd like to see is a to the m over n is equal to the nth root of a to the m, which is equal to the nth root of a to the m. So it's these three that need to be lined up together. And we use either the second or third of those notations depending on what's most convenient, and we're going to see some examples. So here in this example, we've got 256, which is 2 to the 8th power, incidentally, which is also 4 to the 4th power, which is also 16 squared. Anyway, 256 to the 3/4 power is the same thing as the 4th root of 256 to the 3rd power. You see the arrows showing that the 4 from the denominator in the exponent position is the index, and the 3 that was in the numerator position of that rational exponent is being applied as an exponent. And then in green, the 4th root of 256 is equal to 4, and so we move over and see the 4 here. We raise the 4 to the 3rd power and we get 64. Instead of doing this, we could have found the 4th root of 256 to the 3rd power. I would much rather apply the exponent later. Let's take the 4th root of 256 and make it smaller. Let's turn it into a 4 first. Then we can take that 4 and raise it to the 3rd power. I have no interest of putting the 3 as an exponent on 256. So you can see how the order in which those two numbers, the 3 and the 4 from the exponent position, the order in which those get applied, it matters. It matters. All right, so number 2, this example asks us to convert each expression to radical form and then simplify. Great. So we're taking the 9. The 2 in the denominator is the index, so that's a square root, and then we'll raise that to the 3rd power. Square root of 9 is, let's use the principal root and say that it's 3, and then we'll raise that to the 3rd power and get a final answer of 27. To the right of that, we've got 0.09. We're taking the square root of that also, and then raising that to the 3rd power. You can put parentheses around that if you want, and parentheses around that radical. Square root of 0.09 is 0.3, and then if we take 0.3 and raise it to the 3rd power, 3 to the 3rd power is 27. And the fact that this decimal is sort of one place to the left, when we cube it, we end up having to move the decimal 3 places to the left, and so our answer there is 0.027. In part C, we have a negative. That'll get applied last according to PEMDAS. And then the 27, and I've gotten larger in the top left corner. That just happened because my software is freaking out a little bit, and it keeps freezing on me when I'm smaller. Apparently, it wants me to be larger. Don't know. The 3 in the denominator position is the index. The 2 in the numerator is the exponent. Again, you can have this in parentheses here. Don't include the negative inside of those parentheses, though. The cube root of 27 is 3, so there's the negative on the outside, there's the 3 on the inside, there's the square on the outside, so that's equal to negative 3 squared, which of course is equal to negative 9. And then here's another negative exponent. I don't want to talk about negative exponents just yet. So converting between rational exponents and radical notation, we've just been converting from rational exponents to radical notation and simplifying. So this is a slightly more unusual version of what we saw in the previous problems. We've got numbers and variables being raised to different exponents. In the first example, 3 to the 1/3 times m to the 8/3. It's almost like we factored the 1/3 out of the exponent position, leaving us a 3 to the first power and an m to the 8th. And there they are. And then that exponent of 1/3 is being put on the outside of that quantity, and of course an exponent of 1/3 corresponds to a cube root. In the next example, we've got 4 times the 7th root of that quantity. The 7th root with the 5th power, the 5 goes into the numerator position. The 7th root puts a 7 into the denominator as we write the expression using a rational exponent. And number 3 wants us to convert each expression to radical notation. We can do that. Here's the 2x. The 5 in the denominator is the index. The 2 in the numerator is an exponent, so that can go on the outside, or we could write this as the 5th root of 2 squared is 4, x squared is x squared, so we could write this as the 5th root of 4x squared. In part B, I see the -2, and that -2 is not being affected by the exponent of 2/5 at all. So I'm not going to worry about the 2/5 exponent impacting that -2, but I will write down the x. There's definitely going to be a radical here. The 5 in the denominator becomes the index. The 2 in the exponent position could go on the outside, but I'd like to have it on the inside. That didn't really get written as well as I'd like it to. Let me do that one more time. We'll write it as the 5th root of x to the 2nd power. Much better. The 2 goes into the exponent, the 5 goes as the index. All right, here, the entire 9y to the 6 is being impacted. We are taking the square root because of the 2 in the denominator, and we're going to take the result of that and cube it. Can we take the square root of 9? Absolutely. It's a 3, not a 2, but we can do it. There we go. And the square root of y to the 6 is y to the 3, because y to the 3 times y to the 3 equals y to the 6. But that's just the simplification of the square root of 9y to the 6. We still have to cube that quantity. 3 to the 3rd power is 27. That's our new coefficient. And the power rule for exponents, which we're going to see very explicitly written out as a definition, y to the 3rd makes y to the 9th. Not y to the 27th, but y to the 9th. We multiply the exponents. So 27y to the 9. There you go. Convert each expression to an equivalent expression by using rational exponents. So we're going the other direction now. We've been given the expression in radical form. We want to re-express it using rational exponents. So the 2 isn't really part of the mix, so that'll be there. The entire 7x is being affected by something, so let's put that in parentheses. And the index of 3 tells me I need to have a 3 in the denominator. There wasn't an evident exponent, so I'm going to assume an exponent of 1, which makes the numerator of my rational exponent a 1. In the next problem, the x to the 3rd is not being impacted. However, the 6, I don't see an exponent, so I'm going to assume 6 to the 1st power, but I do see that index of 4, so this is 6 to the 1/4 power times x to the 3rd. And finally, the entirety of a squared plus b squared, I had c squared on the brain, so I almost wrote c. A squared plus b squared, that entire expression is being square rooted, and so we'll write it to the 1/2 power. So here are some very well-defined and clearly written out rules or properties of exponents. This is the kind of information that you should have in your notes. And let me see if my software will allow me to cut out of there for a second, so that if you wanted to take a screenshot of this and print it and just tape it into your notes, you may. Otherwise, you're writing it out by hand, which is a fine exercise. And I should not have just turned off my picture-in-picture like that, because, oh, that might be the right size. See if that sticks around. Multiplying like bases, you get to add the exponents, m plus n. When you're doing division, you subtract the exponents, upper exponent minus lower exponent. The power rule, which I mentioned, if you have a thing to a power to another power, you can multiply the powers, a to the mn. The power rule of a product looks a lot like you're distributing the exponent to each of those factors inside the parentheses. And there's a longer drawn out explanation I can give you for why it actually works that way, but it does work that way. The time when it doesn't work is if that a and b right there had a plus sign between them. There's no distributing your exponent over addition or subtraction, but you can, it looks like, it's not what's actually happening, but you can sort of distribute your exponent over multiplication. Or, as it has it, you can distribute your exponents over division also, raising the numerator and denominator to that same power. And then here's the conversation about negative exponents. If you have a to the negative m power, what that negative does in the exponent position is basically totally separate from the rest of the exponent. All the negative tells you to do is to take the reciprocal. So you can see that we have the negative here, but the negative is no longer in this exponent position because we already followed that set of instructions. We did the negative. In other words, we took the reciprocal. So a, which is right here, became 1 over a. And then, now that we have 1 over a to the power of m, that exponent can sort of distribute to the numerator and denominator. 1 to the power of m is still just 1. But a to the power of m, that resides in the denominator. And then there's an example there for you using 8 to the power of 1/3, which is the same thing as a cube root. The cube root of 1 is equal to 1. The cube root of 8 is equal to 2. The reciprocal happened. 8 became 1 over 8. And don't forget that anything to the power of 0 is equal to 1, except for 0. 0 to the 0 becomes a philosophical conversation. So here are some examples using those properties. You are welcome to look through these in more detail. Excuse me. I keep yawning. I had to wrestle with technology and reinstall a bunch of stuff, and it's still being a little bit glitchy, which is why my picture-in-picture is a little larger in the top corner, and I find myself making this video now at 10:45 at night. And I had a whole day already, so I apologize for the yawns. Part A here is showing us the sort of product rule where we have to add the exponents together, 1/3 plus 1/5. Of course, you have to make a common denominator and add those together, ultimately getting an exponent of 8/15. In part B, we're using the quotient rule, doing some simplification there. 8 divided by 4, or rather 4 over 8, reduces or simplifies the same way it would if it stood alone. Dividing numerator and denominator by 4 gives us a 1 over 2. So you can see that 1 over 2 in the answer ultimately over there. And then you've got x to the 3/4 over x to the 7/4, and we're going to do the upper exponent minus the lower exponent. So you see that right here, the 3/4 minus 7/4. Same idea applies for the y values. You've got y to the 1/2 over y to the 2. Upper exponent minus lower exponent says 1/2 minus 2. After creating common denominators and doing the arithmetic, we get the following exponents, x to the -1 and y to the -3/2. And let's just focus in on x to the -1. What happened with it? This x to the -1, now the negative in the exponent position says that we should be taking the reciprocal. So this should really turn into 1 over x with the x in the denominator. And if you look at the final answer here, where's x? It's in the denominator with a multiple of 1 in the numerator. Nice. Okay, so that works out. That does follow the logic that we were talking about just a few moments ago. And what about y to the -3/2? Well, the negative takes the y and pushes it into the denominator. There it is. We've done the reciprocaling. We've done that pushing the y into the denominator, so the negative disappears and we're left only with this exponent of +3/2, and sure enough, there it is. So it takes a little bit of practice to get used to what all of the different characters in this weird little play that we're looking at, what those characters do and how they interact with each other. But if you can remember your rules that we were looking at, or these properties in the yellow box that we saw right up here, right up there. Where'd it go? Yep, it's up there somewhere, that yellow box. Just keep bringing those little individual rules with you and messing around with these kinds of problems, and eventually you'll be able to look at these considerably more efficiently. For example, in part C, inside my parentheses, there's not a lot that I can do. The negative that's in that exponent position says that I could take the x to the 4/5 and shove it down into the denominator. The negative that's in this exponent position tells me to take the reciprocal. Anything in the denominator should appear in the numerator. So the y value maybe should end up in the numerator. But then you've got this negative out here, which tells us to take the reciprocal again. So we just shoved the x into the denominator and the y into the numerator, and then the negative in the exponent on the outside of the parentheses is going to have us take the reciprocal again. And we end up, as you can see with the final answer, having y back in the denominator. So instead of moving everything around just to move it around again, is there a better approach here? And I think the better approach is to sort of distribute this outer exponent to the numerator and denominator. It's going to apply here and it's going to apply here. And when I say apply, it gets multiplied into those exponent positions. Remember that if you have something to a power, you need to multiply those powers. Interestingly though, when you take this exponent and you apply it to the denominator, it still ends up being y to a power, which is the reason you see the exponents being multiplied there also. And from there, it's just simplification of the multiplication happening in the exponent positions, and you get yourself a final answer. Let's look at a couple examples of the kind of stuff that we were just talking about. Well, there's a couple examples. And then there are some application problems, which I'm not going to look at because all of those require the use of a calculator, a scientific calculator. And that doesn't apply to my students because we're not using scientific calculators in this particular course that I'm teaching. So if you'd like some applied problems and you're in a course where you have access to an ebook or some other videos, please go and look at some worked out solution processes there. In the meanwhile, in number 5, I've got a whole bunch of multiplication happening here. And in fact, I could rewrite this as 4 times 6 times x to the 1/4 power times x to the 3/2 power. And then the 4 times the 6, by the associative property of multiplication, I can do that multiplication first and get 24. And then I've got x to the 1/4 and x to the 3/2 being multiplied together. And when I have the same base and we're doing multiplication, what do I do with the exponents? I add them together. So this is times x to the 1/4 plus 3/2, which is the same thing as 6/4. And so we get a final answer of 24 x to the 7/4. All right, so that was a product. Here we've got a quotient. 54/6 reduces very nicely to a 7. Oh, it's not a 7, sorry, it's a 9. I'm tired. And then we have to subtract exponents, upper exponent minus lower exponent, so we have x to the 3/2 minus 1/3. We need a common denominator there in order to do that subtraction. Common denominator is going to be 6. Multiplying the first fraction by 3/3 gives us 9/6, minus taking the second fraction and multiplying it by 2/2 gives us 2/6, for a final answer of 9 times x to the 7/6. So that was sort of a quotient problem. And in number 7, we've got the power rule. We're going to distribute that exponent into the parentheses. This will equal 100 to the 1/2 power times x to the 6 to the 1/2 power times y to the 10 to the 1/2 power. So I've distributed my exponent to all of the factors inside the parentheses. We never distribute exponents into the different terms that are inside the parentheses. Terms would be separated by addition and subtraction, but these factors are connected by multiplication. That does allow for distribution of the exponent. Okay, let's simplify. 100 to the 1/2 power, that's the same thing as the square root of 100, which is 10 for the principal square root. When you have x to a power, or anything to a power, you multiply the powers. 6 times 1/2 is 3, so we've got x to the 3rd here with the y value. Multiplying the exponents there also via the power rule, and we get y to the 5. And that's our final answer there. Number 8's a little bit more tricky. I am trying to move fairly briskly through these. I know usually my lectures are quite lengthy, so I'm just trying to punch my way through these. And if you've been pausing as we've been going along to do a little practice, I think that's a great idea. In number 8, we saw a previous example where everything had negative exponents. So we were taking reciprocals and going from numerator to denominator and vice versa, and then the exponent, or rather the negative in the outer exponent, was undoing all of our reciprocal work that we had done. So in this case, since the only negative I see is in the outer exponent, I'm going to apply it right away and take the reciprocal of the fraction that's in my parentheses. And I'm going to write this next as n to the 1/4 over m to the 7/9, all to the power of positive 4/7 now, because I already used that negative that was in the exponent position on the outside. Now I can distribute my exponent to the numerator and denominator. I'm going to be multiplying, because it's a power to a power, multiplying those powers. So we have n to the, well, let's write it out, 1/4 times 4/7. In the denominator, we're also multiplying the powers that are happening here, because it's m to the power to the power. So we have m to the originally 7/9. That's being multiplied by the 4/7. And then let's clean these up and write ourselves a final answer. In the numerator, the 4's cancel, leaving us with n to the 1/7 power. In the denominator, the 7's cancel, leaving us m to the 4/9 power. That, ladies and gentlemen, is an exploration of exponents in some detail. I hope that's helpful, and I look forward to seeing you next time. Thanks.